Okay, so this is Dr. Sweeney, and I am working on our exam 3 review. Some problems that people had with the quiz, and also anything that we might have as issues that were brought up inside of the journals. So I wanted to start out with this one here. This is from chapter 6, and chapter 6 was on exponentials. And so here's what it says: an unknown radioactive element decays into non-radioactive substances. In 620 days, the radioactivity of the sample decreases by 34%. What is the half-life of the element? And then how long will it take for the sample of 100 milligrams to decay to 92 milligrams? And then it'll tell me the time needed. Okay, so there's a couple of things that I want to get here. Is one is that we have this radioactive element, right? And it says that the sample will decrease by 34%. And one of the things that we want to know is that for radioactive elements, we have a function that actually models those elements. Okay, so that function is P equals P naught e to the RT. Okay, where P is the amount of the element after T time, and P naught is the initial amount of the element. R is the radioactive decay, and T is the time elapsed. Okay, so that's our basic function. You'll notice that it's an exponential function, okay, and that means that it actually grows really fast or it shrinks really fast depending upon whether or not you're getting bigger or smaller. Now, the next thing that I want to do is I want to utilize the information that I've been given, okay, in order to be able to talk about this radioactive element. So it says that in 620 days that the sample decreases by 34%, okay? So how we're going to think about that is we're going to think about, well, I don't know what P naught is, but I do know that I have 0.34 times P naught. That's 34% of P naught, and that will equal P naught e to the R times 620. Okay? And so that's going to be helpful because what that's going to allow me to do is going to allow me to solve for R, which is the last piece that I really need. And then once I get what R is, all I need is an initial amount. Okay? But we're going to utilize this information in order to solve for R. So if I take this and I take 0.34 P naught equals P naught e to the R times 620, then I can just divide by P naught. And what I'm left with is 0.34 equals e to the 620R. And then I just got to use some algebra for logarithms in order to find this. Okay, so in order to isolate R, I'm first going to take the natural log of both sides. So ln of 0.34 will equal natural log of e to the 620R. And if you remember, whenever I take the natural log of e to some power, it's actually going to end up being ln of 0.34 will equal 620R ln of e. And the nice thing is that ln of e is just equal to 1. So that means that ln of 0.34 is going to equal 620R. Okay, now we're going to have to utilize our calculator. So the natural log of 0.34 is negative 1.079, negative 1.079, or we'll use negative 1.0. So that's negative 1.079, and that'll equal 620R. And then, simple algebra, R will end up equaling negative 1.079 divided by 620. All right, we'll just do that real quickly. Divided by 620. And that is negative 0.002, or negative 0.0017. Let's do it that way. So R equals negative 0.0017. Okay. So now I have a model. Okay. So my model is now P, or P of t, equals P naught e to the negative 0.0017 t. Okay, and so that's what it is for this particular radioactive element. Now what I'm going to do is they ask me for this thing called the half-life. So what you need to know is that the half-life is how long it takes for the element to decay in half. So what that means from a mathematical perspective is that means that how long does it take for P naught to go to 0.5 P naught? Okay, because that's half of P naught. And so what I'm going to do is I'm going to put that into my model. So that's going to be 0.5 P naught equals P naught e to the negative 0.0017 t, and then we're going to solve for t. That's the amount of time, right, to find the half-life. Now, a couple of things that you might want to notice. If I've asked for the half-life, notice in the last case, right up here, that I took 0.34 P naught, okay, and I divided it by P naught, so I ended up with just 0.34. I'm going to do the same thing here. I'm going to divide by P naught, so I'm going to end up with just 0.5 equals e to the negative 0.0017 t. And it turns out that that's just fine, okay? So in this case, because we're given like no specific starting amount, okay, we can actually just assume that we're going to get half and we can put in as a 0.5 instead. So now I've got this. Now what I'm going to do is just like in the last problem, I'm going to take the natural log. So natural log of 0.5 is going to equal the natural log of e to the negative 0.0017 t. Okay. And so that means that natural log of 0.5 will equal negative 0.0017 t ln of e. Okay, and so hence just ln of 0.5 is going to equal negative 0.0017 t. So now we'll utilize our calculator. 0.5, I'll take the natural log. Okay, and then I'm going to divide that by 0.0017 negative, and that gives me 407 days. So I end up with t will equal negative 407. Well, actually, negative 407.734. 734, or approximately 408 days. Okay, so that's the first question. Now the second question, now that I have my model, the second question is even easier than the half-life one. It asks, how long will it take for a sample of 100 milligrams to decay to 92 milligrams? So I'm going to go back here and I'm going to say, okay, well now P naught equals 100 and P of t will equal 92. We'll say milligrams. So I can set up my model. So 92 is going to equal 100, right? Because we're going to put that in for P naught, e to the negative 0.0017 t. Okay. Now we're just going to do some algebra. And so that means that we're going to divide up through by 100. So 0.92 is equal to e to the negative 0.0017 t. Take the natural log of both sides. So negative 0.0017 t, natural log of e, is going to equal ln of 0.92. And so the ln of e goes away because it equals 1. And let's go in and use our calculator. We'll take the natural log of 0.92. And that's negative 0.0833. Equal, excuse me. Okay. It's negative 0.0083, so that's that. Negative 0.0833 equals negative 0.0017t. And we'll divide. So that equals 49 days. So t equals 49.048 days. 48 days. Or approximately 50 days. Approximately 49 days, actually. Round down. Okay, so just to review, what we first want to do whenever we're dealing with a problem like this is we want to go in and we want to say, okay, I have this model, and here's our general model for an exponential. Okay, where P is the amount of the element after T time, P naught is the initial amount of the element, R is the radioactive decay, and T is the time elapsed. Then what I'm going to do is I'm going to take some of the information that I'm given inside of my problem in order to set up my problem. Okay, and in this case, we wanted 34% of the original amount, so 34% of P naught, okay, this thing right here, is going to equal then P naught E to the R, and it tells us that it takes 620 days. Then I'm going to use that information and what we know about exponentials in order to solve for R, my rate. And once I find what R is, okay, once I find what R is, that's actually going to then allow me to have the complete model. Something to remember about solving for R is to take the natural log of both sides in order to get rid of the exponential. Okay. Then once I figure out what R is, I just need to remember what it means to have a half-life. Okay, so a half-life is how long it takes for the element to decay in half. So, consequently, we're going to find our 0.5 of the original amount, which, by the way, we don't even need that P naught. Right, we talked about that. Then do a little bit of algebra to find what T is. Same thing here when we're asked to find the specific amount left after a either a specific amount of days or to find how long it takes for a specific amount to come to get a specific amount using our model. And that is, again, just utilizing that general model for the exponential. All right, so that completes our video.